Essentially, algebraic topology translates a problem of topology to a problem of algebra, solves it, and then draws conclusion about the original topological problem. In this module, we shall simply use intuitive understanding of topological concepts and see where algebraic topology gets into the picture. We begin our discussion by picking up just one situation from a wide range of problems where topological methods are either inadequate or difficult to use. Let us take a very fundamental question. For m not equal to n, is an Euclidean M space topologically same with an Euclidean n space? Now, first of all, what do we mean by topologically same? Informally, topological sameness means that whether two topological spaces are homeomorphic or not. Intuitively, we all feel that the answer is no. But in general, it is very difficult and perhaps impossible to answer this question by applying the techniques of point set topology. In fact, for large values of m and n, there is no topological method by which this result can be established in general. We generalize this problem for any two topological spaces x and y. As we have already mentioned, informally speaking, two topological spaces are topologically same if and only if they are homeomorphic. So the question takes the form, is x homeomorphic to y? This is an important and fundamental question in general topology, and it is sometimes referred to as homeomorphism problem. We now observe several situations where topological techniques may be useful for determining this sameness of two topological spaces. Let us take an example. Suppose we are given an open interval, that is a line segment without its endpoints, and a semicircular arc without its endpoints. We claim that these two are homeomorphic. How do we prove it? An open interval is nothing but a line segment without its endpoints, whereas a semicircular arc without its endpoints is a bended line segment. So intuitively, we feel that if we simply flatten the circular arc into the straight line, then that will give us the homeomorphism. So that actual correspondence is seen here. Given a semicircular arc, suppose this is the semicircular arc, and suppose this is the line segment. We draw a line through the center of the semicircular arc that intersects both the objects. Now this line cuts the semicircular arc at the point x and the open interval at the point y. And this correspondence we can map x to y and y to x. So we can think of a function which maps the point x to the point y, and this function is certainly bijective because there is no other point where y goes back to. Now let us take another example. A circle is not homeomorphic to an open interval. Now this time we have to show that two things are not homeomorphic. Simply removing a point from the circle transforms it to a single line segment. On the other hand, removing a point from the open interval breaks the open interval into two pieces of line segments. A single line segment, that is a space with only one component. In topological terms, this is what we call connectedness. This line segment cannot be homeomorphic to two pieces of lines. That is a space with two components. In topological terms, what we say is that the space is disconnected with two components. And consequently, the original figures are not homeomorphic. See, in the next example, we apply the same technique. Given the real line R and given the plane R2, we have to show that R and R2 are not homeomorphic. We apply the same technique. We remove a point from R that breaks the real line into two components. Hence, punctured R is disconnected, but R2 is still connected when a single point is removed from it. A connected space cannot be homeomorphic to a disconnected space, as connectedness is a topological property. And so, the original spaces, that is R and R2, they are not homeomorphic to each other. In fact, in this last example, there is nothing special about R2, and so the same arguments establish that Rn for any n greater than 1 cannot be homeomorphic to the real line R. But it is not possible to argue in the same line to obtain in general that Rm is not homeomorphic to Rn for any m not equal to n. So here, mere topological techniques is either inadequate or difficult to establish that Rm and Rn are not homeomorphic. In the next example, we take a sphere S2 and a torus that is S1 Cartesian product with itself. If we look at the shapes, this is a torus, it looks like a tire, and if I remove a circle like this vertically, then what do I get is just like a pipe-like structure. This new shape remains connected. But in case of a sphere, if we simply remove this circle, then we are going to get two hemispheres, that is two components. Hence, by applying the same argument, we can say that the torus and the Euclidean two-sphere, they are not homeomorphic. Unlike the case of a two-sphere and a torus, it is highly difficult even to prove that S3 is not homeomorphic to S1 cross S1 cross S1. So once again, topological methods are inadequate to solve this kind of problem, that whether Sn and S1 cross S1 cross S1 up to n times are homeomorphic or not. Algebraic topology partially solves this so-called homeomorphism problem. Mind that I am saying it is partially solving the problem. Now, what algebraic topology does? This algebraic topology basically aims at creating and defining various algebraic objects associated to topological spaces and homomorphisms induced by continuous maps. Now, let us just look at the scheme. This gives us the general scheme as follows. To each topological space X, associate an algebraic object Hx. If there is a continuous function from X to Y, where X and Y are topological spaces, then that continuous function induces a homomorphism between Hx and Hy. If the induced homomorphism, that is the homomorphism from Hx to Hy, is not an isomorphism, then the given topological spaces are not homeomorphic. Now see, this problem is one-sided. Why? Rather, this solution is one-sided, because if two topological spaces X and Y are given and we know that they are homeomorphic, then only we can conclude that the corresponding induced homomorphism between Hx and Hy becomes isomorphism. But the converse may not hold. That means, if we have an isomorphism between Hx and Hy, we cannot say, we cannot claim that there exists a homeomorphism between X and Y. Given a topological space X, we want to associate an algebraic object Hx with that given X. Now the question is, how do we get that algebraic object? The purpose of this course is to know certain method of construction of that algebraic object. In this course, we shall learn how to construct fundamental groups. For that matter, we will study homotopy theory, and we shall also study simplicial and singular homology to get homology groups for associating it with the given topological space. Let us now discuss another very important problem of topology. This problem is called lifting problem. Suppose we are given a continuous surjective function from a topological space X tilde to another topological space X. Also, suppose there is a function f, which is again a continuous function from another topological space Y to the topological space X. The question is, does there exist a continuous function g from Y to X tilde such that the composition P compose G is equal to F? This problem is referred to as lifting problem in set topology. If such a map G exists, then this G is called a lift of the given map F. So we restate this problem in terms of commutativity of the diagrams. Suppose this diagram is given. This diagram consists of 3 topological spaces, Y, X and X tilde, and 2 continuous functions. One is F and the other one is P. Moreover, this function P is surjective. Question is, does there exist a continuous function G from Y to X tilde such that this complete diagram commutes? It can be established that the commutativity of the diagram of groups and group homomorphisms determines the commutativity of the diagram of topological spaces and continuous maps. Now, what do we mean by that is, if suppose we have a diagram, commutative diagram inside the collection of topological spaces and continuous functions, can we shift this problem entirely to the algebraic topology setup? That means, can we associate Hx tilde and an algebraic object with the topological object X tilde, Hy an algebraic object with the topological object Y, and an algebraic object Hx with the topological object X, such that the corresponding induced homomorphisms give the second triangle, that means the triangles within the framework of algebra, commutative. And the question is whether the converse of this is also true or not. It has been seen that this lifting problem can be resolved by the techniques of algebraic topology entirely. That means, if I get a commutative diagram in topological spaces, we get a similar diagram in algebraic setup. On the other hand, if a diagram is given in the algebraic setup, we can shift it back to a diagram in the topological setup. We shall eventually show in this course that the fundamental groups, the simplicial or singular homology groups which we are going to construct, are all examples of functors. By this, we want to end this module.